Today we shall be discussing about the binary phase shift keying circuit, the modulator for Bpsk as well as the demodulator for Bpsk. So let me open the Bpsk KiCad project and then the schematic editor. So I already have drawn this modulator and demodulator circuit. So I have the modulator circuit over here and then the demodulator circuit over here. I am using this balanced modulator approach. So this much region is basically the balanced modulator, and some people call this as a ring modulator as well, due to the arrangement of these diodes in a ring fashion. So if you follow these connections, you can see it's in a ring. So this is one very good circuit that you can use for Bpsk modulation as well as the demodulation. So in here for the demodulation, I have an exact copy of the same circuit. So for this this modulator, I am feeding the carrier signal at this transformer input, and then connecting the message signal, which is a digital signal between these two secondaries. So this is a sine wave. Let's see the specification of this one. So it's a it's a sine wave with an amplitude of 500 millivolt and the frequency of 101 kilohertz, and all the other parameters to be 0, and that is connected to the primary of this transformer. And then I have this digital source. So what I have here is a pulse generator with a pulsed value of 1 volts and the initial value. So the peak value will be, the positive peak will be 1 volts and the negative peak will be -1. So ones will be represented using 1 volt and zeros will be represented using -1 volts. And rise time, fall time, all of very negligible value, and a pulse width of 50 microsecond and a period of 100 microsecond. So this will be a 10 kilohertz data stream with a 50% simulated using a square wave of 50% duty cycle. Okay. And then these diodes, I am just loading this 1N4148 library that I have downloaded off the internet. And the only other component worth mentioning is this transformer, which I am modeling using a sub-circuit that I have created by myself. I have added another video as to how to create sub-circuits for such components by yourself. So I am just using the same sub-circuit here to model the transformer. So I am picking that saved definition as a transformer 1p ss.lib. I am just loading that and indicating that to be a sub-circuit, and then I am using it as it is. Both the transformers are modeled using the same sub-circuit. And so how the circuit works is, so this is basically a sine wave modulating, or the carrier signal, and that's going to be, you know, coupled into the secondary part of this transformer. And this will provide a 1 volts when at this point when it is logical 1, and in that case the signal at these 2 points will be passed on directly to these 2 points. These diodes will get forward biased. So these 2 diodes will get forward biased, and these 2 will be in reverse bias. This potential, the potential here is 1 volt, and the potential here will be 0 volts. So these 2 diodes will get forward biased, D3 and D2 will get forward biased, and D1 and D4 will be in reverse bias. So the connection will be a direct connection to the other transformer. So when the symbol is 0, we are going to generate a -1 volt here and a 0 volt here. So the -1 volt will forward bias this diode and this diode. Okay, so the DC -1 volt will forward bias these 2 diodes and reverse bias these 2 diodes. So effectively the connection is this node of this transformer will be connected to this node, and this node of the transistor will be connected to this node. So it's basically cross connecting. Okay, so if it is a logical 1, it is connecting directly these 2 transformers, and if it is a logical 0, it is connecting in a cross connected fashion. Okay, or we are doing a 180-degree phase reversal when it is a logical 0. So that's how this circuit works, and we have just a current limiting resistor connected to this voltage source, or otherwise if we don't have that, then we will have very large amounts of currents flowing through these diodes. And the secondary side of this transformer is used to collect the signal, the Bpsk modulated signal. And on the demodulator side, so if you look at this modulation from a different perspective, all we are doing is multiplying the carrier signal at a higher frequency. So this is at 101 kilohertz, and this is at 10 kilohertz, or 10 bits per second maximum bit rate. And we are just multiplying these 2 signals together to create this Bpsk. Let's first see how the Bpsk waveform looks like, and then we will talk about the demodulator. And in addition, I have used this simulation definition here. So I want a transient simulation with 10 nanosecond steps for 200 microseconds. I want to collect the data from the 10th microsecond, discarding the 0 to 10 microsecond duration where the circuit tries to settle to the steady state. So let us simulate it. So I'll have that simulation conditions already populated here, and let me run simulation. So the simulation is complete, and let's probe these some of these points. So I want to see the carrier signal I want to see the message signal, and I want to see the modulated Bpsk signal. 3 signals I want to observe. Okay, so the message signal is in the green, so it swings from 1 volt to -1 volt at 10 kilohertz rate, and the carrier signal is in red, and you can see that it is a continuous stream of this continuous sine wave stream, and the Bpsk signal is in the blue color, and you can see that the phase reversal during this transition between the message signal being 1 and message signal being 0. So to illustrate it proper, let's see if we can pick Bpsk with a different color. Okay, so now we have the Bpsk signal in yellow, which is much better visible, and the carrier signal is in this purple color. So you can see the carrier signal is basically a continuous stream of sinusoidal wave, and the Bpsk signal will have opposite phase, 180 degree out of phase with the carrier signal when we are signaling a 1 value, and when we are signaling a 0 value or 0 from message stream, it will be in phase with the carrier. So the message stream, the Bpsk message stream is there right behind this purple line, and at this message symbol transition times we can see a phase reversal happening. So I'll hide this carrier signal, and then you can see the phase reversal, just the Bpsk signal and the message signal in the screen. So at these transitions you can see a 180 degree phase reversal happening. Okay, so this is the Bpsk, this is the expected Bpsk waveform. Okay, so let's come back to the circuit, and let us see how the demodulator is set up. So I have said that the other way to look at this circuit is as a multiplier. So when the message signal is 1 volt, you are multiplying this sine wave with 1 or with -1, whichever way, and when it is when it is -1, you are multiplying it with -1. So when it is positive 1 volts, you are multiplying it with positive 1 volts, the carrier, and when it is -1 volts, you are just inverting the this signal stream. So you are multiplying this voltage with this voltage. That's all that this circuit is doing. And if you take that perspective, then in order to decode this Bpsk stream, what you can do is you can multiply it with the carrier signal itself. So during the regions where it is out of phase with the carrier signal, the multiplicator, the product will give you a negative voltage, and during the regions where it is in phase with the carrier, you will get a positive voltage. So multiply this signal with the carrier itself, exactly the same phase carrier itself, and then you can demodulate this signal stream, this message stream. So that approach is what I am using. So I will be providing the carrier signal to these two ports, and I will be feeding the Bpsk signal here itself. And the carrier I am taking it using this label, and I have defined the label here as well. So this point where I get the 101 kilohertz sine wave, this is one point is grounded and the other point is connected to this label C. So the same way, one point of the transformer, or one point of the balanced modulator is connected to ground, and the other point is connected to label C, and then a current limiting resistor, just as we did in this case. A signal source connected between ground and the the current limiting resistor. So exact same topology we are using here also, and then out here we should have the demodulated signal, which I am then filtering using an RC low pass filter, because this will be a baseband information that we will be getting here, and it will have frequency spread from 0 Hz. It can have frequency spread from 0 Hz to say 10 kilohertz, and therefore we cannot use a very sharp band pass filter or band reject filter. So we have to use a low pass filter itself. You can use a higher order filter using LC circuits, but what I am using for simplicity here is a first order RC filter, and the design of this filter will be pretty easy. You have to accept anything below 10 kilohertz and have to reject signals above 10 kilohertz. And let us then see the signals at this point and at this point. So we have the message signal and the Bpsk modulated signal already populated here. In addition, let us see the signal at this point and at this point. This V of D will be the demodulated signal. Okay. So we have not taken in V of D yet. Okay, so the signal at the output of the balanced modulator, this net R5 pad 1, shall be this point. So at this point the waveform is in the cyan color. So if the signal is in phase with the carrier, then you will have them multiplied together and you will get positive values, and if these are in out of phase you will get it multiplied together, and you will get large negative values, and that's happening, and then we are filtering it and collecting the baseband information. So after at the filter output, the output demodulated voltage is shown in this white color, and you can see it is tracking very well with the message signal itself. And for clarity, let us remove this intermediate signal, and you can see that it is tracking somewhat accurately. And if you have these higher order filters, then you will get a you will be able to detect better. Let's increase the frequency a little bit, and then increase the carrier frequency a little bit to a more realistic value, and then let's do the simulation. So 10x the current carrier frequency. Save the schematic. Let's move on to the simulation window, and let's run it once again. So now we have a better demodulated output waveform. So I'll remove the Bpsk signal, and a waveform, the demodulated output waveform and the modulating signal alone in the screen. And from this it is clear that we can easily convert this into a 1/0 format or defined voltage levels with the help of a comparator with fixed thresholds. And so we have achieved the demodulation of this the Bpsk signal. So this is the demodulator. This is the demodulator and the modulator for the Bpsk signal.